MBSE is an upgrade of traditional systems engineering. It helps boost quality, reduce costs, and lower risks. All things that traditional document-based approaches struggle to keep up with. Before diving into the key benefits of MBSE, let's have a look at the return of investment. This here is the life cycle cost of a program over time. Systems engineering looks like this. We see that the majority of the cost occurs quite late in the life cycle. This spike is due to the challenges of traditional systems engineering that we explored in the previous videos. Now here's the curve for model-based systems engineering. It does require an initial investment. There's the cost of defining methodologies, implementing them into tools, infrastructure, training people, and so on. But the payoff is quite huge. Thanks to early error detection, reusing validated models, improving communication and traceability, we directly reduce rework, shorten development cycles, and lower overall system lifecycle costs. And this is valid for the very first application of MBSE. As MBSE becomes widespread, the initial spike is going to decrease. In industries like aerospace, defense, and energy, where systems are becoming more complex by the day, MBSE has proven to be an absolute game changer in reducing errors, improving system quality, and keeping projects on track. Let's look at some specific areas where MBSE shines. First up, one of the biggest benefits of MBSE is the separation of representation and presentation. Think of it like this. The system model captures the true essence of a system, and it allows you to present the data in many different ways. Let's say you are a systems engineer, responsible for a propulsion system on a tanker. You only care about certain aspects of the system and you want to see only what is relevant to you. If you are dealing with navigation aspects, you will need different kind of information. You don't care how propulsion works, at least you don't need to dive into all the details. Here's the beauty of MBSE. Everybody gets their own view of the system. We're all looking at the same system model, but from the lens that's most relevant to us. Whether it's project timelines, technical requirements, or specific components, each person has the data they need. This is huge, because in traditional document-based approaches, the two are usually mixed. Documents contains the engineering data, but it is not adapted to everyone looking at it, meaning you often end up with the same information repeated across multiple documents, which leads to confusion, mistakes, and consistency issues. With models, it's like having a single source of truth that everyone can rely on. Views are so useful to systems engineers that standards exist to define them. An architecture framework organizes viewpoints and views in a way that allows stakeholders to easily access the type of data they need. It's especially useful when multiple stakeholders from different companies are involved, like in government or defense projects. Each company may have its own tools and methodologies, so an architecture framework helps align everyone to communicate effectively. An example is the Unified Architecture Framework, UAF for short. Each box in the grid is a specific view of your system or project and specifies what kind of data is expected. The standard gives you recommendations in the format of the data, but you can use either documents or models when somebody asks for a specific view. Now these are integrated by tool vendors, so you can model within those frameworks if necessary. One of the key strengths of MBSE is that models can be as simple or as complex as the project needs. As the system development evolves, the models get richer and more detailed, and this facilitates optimization and trade-offs. In the early phases, we might start with simple views and equations that help define high-level concepts or basic performance metrics. These models are quick to build and provide a rough understanding of how the system will behave. You're using models to make broad, high-level decisions. Then, as you go deeper, you'll start looking at the behaviors in more details, a bit closer to reality. The models get more granular, and decisions become more specific and optimized. By the time you're deep into the design, you could be running complex simulations. The models are as close to reality as it can get. It helps engineers understand how the system behaves under real-world conditions without having to wait for a physical prototype to even exist. MBSE allows to make trade-offs using real data and simulations at a lower cost because everything is digital. You will still need to have physical mock-ups and prototypes, but by the time you need them, you should be quite confident in the decision taken so far. Now let's talk about early error detection. We all know this famous graph which shows that the further you get, the more expensive it is to fix a mistake. You catch a problem early, it can be relatively easy to fix. You catch it late and it becomes a nightmare. With traditional systems engineering in today's world, errors often get spotted too late. But with MBSE, it's a completely different story. Models allow systems engineers to refine early stakeholder requirements and design aspects in a more precise and rigorous way. With model execution, we can validate our specification early on, and we can even involve stakeholders in the process since we can make dedicated views for them. We test our assumptions up front, avoiding costly mistakes or misunderstanding, which saves time and money. Then the models are continuously and automatically checked against various criteria. For example, the system model can perform consistency checks, making sure everything's connected right and works as expected. A little oversight here can cause a whole heap of trouble down the line. MBSE helps prevent that. Plus, if the models are set up correctly, they can even ensure the engineering process and associated methodology is being followed properly, checking if any steps are skipped by engineers, which could be costly down the line. Let's move on to impact analysis, which is a real game changer. In any system, changes to one part can affect others, sometimes in ways you never expect. With MBSE, if you have a strong framework and if everyone plays along, you can instantly see how a change in one area will ripple through the rest of the system. Whether it's a technical tweak, a regulatory update, or even a new stakeholder request, MBSE helps you visualize the broader impact. Finally, one of the most frustrating things with traditional systems engineering is that a lot of project feels like it starts from scratch. During the development, hundreds of documents are produced. You end up drowning in documents, and previous design choices are hard to find or reuse. So when a new project starts, you start over. But with MBSE, it's a whole different story. MBSE makes it easy to reuse models and components from past projects. Since everything is well documented, rigorously traced in the system model, you can easily see what parts can be reused and why certain design choices were made. Plus, MBSE lets you create libraries of reusable assets, like off-the-shelf components, signals, and other system elements. These can be applied to future projects, saving time and reducing the risk of errors.